In this video, we'll be talking about just the basics of what a function is. So to begin with, a relation is a way to match up objects. What does this mean? Well, for instance, if I had 1, 2, 3, we'll just have 3 objects here, and let's have the letters A, B, and C. We can match this up any way we want. Namely, we could let 1 go to A, we could let 2 go to B, but we could also let 3 go to B. On the other hand, we could also just let 1 go to B as well. Why not? But the big point here is there's no reason why everything here needs to be used, and there's not any reason why everything here needs to be used, and there's no sort of rules in general for a relation dictating whether how many times different objects go to other objects. Okay? With that said, a function f from a set A called the domain, which is the set of inputs, to a set B, which contains the range, which is the set of outputs, is a relation which assigns to every one element x in A only one element in B. Now, the top up here would not be a function. And the basic reason why it's not a function is because of this right here. You can't have, for a function, you cannot have an element in your domain, which would be here. This would be your domain. You cannot have an element in your domain going to more than one element over here. By the way, the elements that get hit over here is called the range. Okay? But what about, so what would be an example of something that would be a function? So something that would be a function is something like if I had 1, 2, and 3 here, and I had A, B, and C. Something like 1 goes to just B, 2 goes to A, 3 could also go to B. Why not? That actually would be a function because every element in the domain is used, and you also have that each one only goes to a single value. Okay, so even though both 1 and 3 go to B, that's fine because for 1 you just get B, and for 3 you just get B. So to summarize, there are actually 4 different rules for functions. The first rule is that each element in A must be matched with an element of B. That is, every element in your domain must get used. The second rule is then that some of the elements in your in the set that you're going over to may not be matched with any element from your domain. Okay, so not everything needs to be hit there, even though everything in A needs to get used. Thirdly, is that 2 or more elements in A may in fact be matched with the same element in B. Namely, for 2 different inputs, so to speak, you can get the same output. Indeed, we saw this with the last 2 examples that we saw. Finally, we have that an element in A, aka the domain, cannot be matched with 2 different elements in B. That is, the way we're going to say this again and again and again is that for every input, there's exactly 1 output. And that is sort of the golden rule of functions. All right, with that being said, there's also 4 different ways to represent a function. The first way is verbally, which is by using a sentence that describes how the input variable is related to the output variable. The second way is numerically, which is by using a table or a list of ordered pairs that matches input values with output values. The third way is graphically, where we use points in a coordinate plane where the horizontal positions represent our input values and the vertical positions represent the output values. And finally, the last way is algebraically, which is using an equation in 2 variables. In practice, we'll see that we'll use graphical and algebraic representations throughout most of the course, but it is good in practicality and the real-world applications to think verbally and numerically as well about functions. All in all, the way to think about a function, so here I talk about inputs and output variables. The easy way to think about a function is as a drink machine, where you have your buttons, namely the inputs, and when you put one out pops your output, right? Input, and so these are all of our inputs. Of course, if you press this button, you expect to get an output, right? And you expect to get the same output each time. However, if you press different buttons, you might get, so sort of different buttons could give you the same output. Also, every button needs to be pushed, right? But of course, not every single different type of drink on the planet is going to come out of here. So let's go through and look at each of these different ways of representing a function in detail with some examples. So first, verbally. For example, does the following represent a function? The input value x is the number of representatives from a state, and the output value y is the number of senators. Well, it turns out that it does. And the reason why is that here you sort of have all your inputs, and here every single input has a unique output to it, okay? Namely, no matter what the number of representatives is from a state, the output value y is going to be 2 because every state has exactly 2 senators. By the way, that means this is really, the function in a sense is really just 2. No matter what you plug into it, you get 2. This is called a constant function. Because no matter what value you put into it, you always get the same value back. And so the output is constant. And now let's talk about representing function numerically. So let's see if the following represent functions. The first one does not, and the reason why, so no, and the reason why is because 2 gets sent to both 10 and to 11. Okay? So that immediately disqualifies it from being a function because the same input has 2 different outputs. Here, however, we also have a no for a similar reason, namely, -1, the same input, gives us 2 different outputs. Same problem. However, let's go ahead and have you try C. So, on the count of 3, I'll reveal the answer. 1, 2, 3. The answer here would be yes, as every input has exactly 1 output, right? 0 only has the output -4, 1 only has the output -2, 2 only has the output 0, 3 only has the output 2, and 4 only has the output 4. And now let's talk about how to represent functions graphically. So the question here is, does the following represent y as a function of x? The answer here would be yes, and the reason why is because you can consider this as a list of ordered pairs. Namely, this is the ordered pair, what? -2, 3. This is the ordered pair -1, 0. This is the ordered pair 0, -1. This is the ordered pair 1, 0. And this is the ordered pair 0, this is the ordered pair 2, 3. Which means that we could write this as a list of ordered pairs, thinking sort of numerically about it. -2, 3, -1, 0, 0, -1, 1, 0, and 2, 3. And what we notice here is all of these, -2 only has the output 3, so in a sense, -2 only goes to 3. -1 only goes to 0. 0 only goes to -1. 1 goes back to 0, but that's okay. And 2 goes to 3, which is also still okay because you can have the same output for different inputs. You just can't have different outputs for the same input. So, yes. As a preview, we're going to see in the next section that we can use something called the vertical line test to test this. And the vertical line test is going to make this a lot easier. Finally, we have what is going to be our focus for the rest of this section, which is representing functions algebraically. For a bit of terminology first, if y is a function of x, then we say x is the independent variable and y is the dependent variable. Why does this matter? The reason this matters is because essentially our independent variables correspond to inputs, and our dependent variable depends on what input you put in, and thus it is an output. Okay? So, for example, let's determine whether each of the following equations represents y as a function of x. We can do this by solving for y and seeing what we get. Here we have y equals 1 minus x squared. And this is a function. And the reason it is a function is because no matter what we were to plug in for x, we would always get a single y value. So for any x, just one y value. And thus, the golden rule is set for functions is satisfied. For any input, we get just one output. Over here, on the other hand, if we solve out for y, or try to solve out for y, we end up with y squared equals 1 plus x. But if we then we have to take our own square root, and when we do that, we have to put in the plus or minus. Well then, this is not a function. And the reason this is not a function is because if I were to plug in, for instance, 0, if x equals 0, then I get two outputs. So y equals what? It equals plus or minus 1. So this violates the golden rule, which is for a single input, I got two different outputs. And now it's time to have you try an example. So determine from the following two whether each equation represents y as a function of x. On the count of 3, I'll reveal the answer. 1, 2, 3. So the first one would not be a function because solving out you get y equals plus or minus the square root of 8 minus x squared. So this is not a function. The plus or minus is sort of the key here, and that for some x values you could get two different values. Namely, if x were equal to 2, you would have x squared is 4, 8 minus 4 is 4, square root of 4 is 2, so y would be plus or minus 2. On the other hand, if we look at this one, we get y equals 36 minus 4x squared. This means there's no way we could get more than one y value for a single x value plugged in, which is explained right here. For more practice in working with the 4 different representations and the basic rules for functions, be sure to see page 44 of the textbook and work problems 1, 2, and 5 through 18. In our next video, we'll talk about evaluating functions.